This week's topic, kind of like what we covered at the end last week, is dynamic programming. I asked you, if you could, to try to watch the coin change example that I recorded, and I saw fewer than 10 people have watched it so far. So I'm guessing most people have not actually seen it, which is going to make today's demo a little bit weird. And if you go back to watch this later, I would recommend watch the video that describes it first, and then watch the coding of it. Okay, so the idea of dynamic programming is that you are not resolving subproblems. You're phrasing a big problem in terms of things that are smaller, that you solve one time and you remember in one way or another. Okay, and the key for pretty much all dynamic programming problems that we have is you're going to write some sort of function, and I usually write it dp. That's just my note. So dp, and it might just have one parameter. It might be dp of a, or it might be a 2-parameter problem where it's dp of a, b, or it might be a 3-parameter problem with a and b and c. And you could actually have an arbitrary number of parameters, but the more parameters you have, the more limited you are in kind of your options. And so regardless of which one of these you have, you're going to make a recursive definition of dynamic programming. So this should describe a state of the thing that you want. And then you should be solving for some element of the state. Okay? And each solution that you have should be phrased in terms of simpler things there. So you should be able to describe a recursive definition for it. And again, if you haven't watched the videos, watch the coin change, watch the knapsack ones. Those are 2 examples that show exactly how you set this up. So I go into a lot more detail in the coin change one, a little less detail in the knapsack one, but watch those if you haven't. Okay, so the idea here for the coin change problem is we are going to set up something. Okay, so sorry. So we define dp by dp of something that's like another value that's like a minus 1, for instance. Okay, and when we talked about like Fibonacci numbers last time, we would compute dp of a minus 1 and dp of a minus 2, and we would add those together to get dp of a, if you remember. And there always has to be a base case also. So you have some recursion and you have some base case or base cases, and everything gets defined that way. Okay, so let me describe the coin change problem since people didn't exactly watch it. So for coin change, the question is, how many coins minimum to make change for some amount x? Okay, so I'm going to have some amount x, and I want to know how many coins do I need to, at minimum, to make change. And so depending on the denomination of coins, changes whether this could have a greedy solution or it might not. So an example, and it's a very simple one, so we'll use it. An example is if you have coins in denominations 1, 3, and 4, and if you're asked for 6, a change of, like to make change for $6 or 6 units of money. Okay, if you use a greedy solution, the greedy solution would give you a 4, and then a 1, and then a 1, but the optimum is 2 3s, right? Okay, so the correct answer for the minimum is 2. That's the answer that you want to get. Okay, now if you look at the, sorry. Give me 1 second. I've got to create a new blank screen and share it. Okay, now if the coin change problem, what we're going to do is we're going to have a list of values. Okay, and the values, sorry, I need to open up the chat window again. All this goes away. Okay, the value of the coins is going to be the values of each one of them. We'll just keep that in an array. So for instance, we might have the array 1, 3, 4. If we have 3 coins of values 1, 3, and 4. But this could be arbitrary. You know, we could have coins like our coins that have 1, 5, 10, 25. There's actually 50-cent pieces and dollar coins and stuff like that. Okay, so depending on what we have, you just have some list of values. And those values, I'm going to, at least in my coding example, I think in the example I did before, I called these 1 through 3, but this will be 0, 1, and 2. Okay, and so we are going to set up a dynamic programming problem so that dp of a, b, this is going to be the minimum number of coins to make change for the amount A using coins 0 to B. Okay? And if there are a total of n coins here to choose from, the solution, the thing that we are looking for, is going to be dp of the amount x that we read in, however many dollars we need to make change for, and n minus 1, since they're numbered 0 to n minus 1. Okay? So we have all those coins available. Those are the ones available to us. So that's going to be our solution. And the way we can set this up is we can set up base cases. So if we need change for $0, no matter what it is, the answer is 0. And if we ever need change for some amount A that's greater than 0, and we have no coins, anything negative here, then this is going to be some number infinity. It's going to be too big, something that we can't actually return. And then otherwise, we've basically got two problems, or two options. So our normal non-base case is that dp of a, b is going to be the minimum of two options. So the first one is we use a coin of value b, and so then we are left with a new dynamic programming problem that has the amount that we need now is a minus val of b, whatever the value is. And we still have coins from 1 to b to choose from, and we've used one coin. The other option is we choose not to use a coin of value b, which means we still have a problem of size a, and we're left with one less coin to choose from. Okay, so all of this, that's like the quick repeat of what I went over in the video, but since I know very few people saw it, hopefully that's like a quick intro to this. Okay, so I'm going to show you, I went through an example, I showed you a table of how to build it up. I want to show you some ways you can code up dynamic programming problems like this. It should remind you of what we did with the Fibonacci numbers last time. Some of what you see is going to be similar, but it'll be a little bit different. There'll be some differences there. So let me switch over to share code. Okay, so I'm going to just start out. Okay, so start out with our basic program. And what we're first going to do is we're going to read in the set of values of coins that we have. So I'll call that something like num_c, the number of coins that I have here. And I'll read that in so that we know how many coins we have. And I'll call this x. And I'm probably going to need a j eventually, so I'll just go ahead and create a j. And then I'll just go through and read all of those. For I equals 0, I is less than num_c, I plus plus. And I'm going to actually have to create this. I want to read in something like val sub I. So let's go ahead and create a vector here. Vector of int val. And after I've read in num_c, I will resize val to be of size num_c. So however many coins I have. Okay, so at that point, so that's one way I could do this. Another way I could do it is just read them in one at a time and push it to the back of the val array. So that's one option. Another option would be, instead of reading in val sub I, I would read in x and say val.push back x. Okay, but either way, I'm just reading in the coin values into the array val. Okay, so if there were 3 coins, num_c would be 3, and I would read in, say, like 1, 3, and 4 was the example I had before. Okay, so now I have my value there. So I'm now going to read in the amount of money that I want. So I'll create a variable amount, which is the amount that I want to get change for, and read that in. And I'll just make this a loop so that I can just keep repeating this over and over. Okay, so I'm just going to keep in reading in amounts and doing this problem as long as it's there. And then what I want to do is I want to output whatever the minimum number of coins is. So I'll create a function dp, and I want to give it amt and num_c minus 1. So if you remember before when we defined our recursion, this is going to be our base case that we have along the way. So now I need to create my function dp. This is going to be my dynamic programming function. So before I go on, just to make sure, this first part of what we did up here is we're going to, all of this is just to read in the coin values. Okay. And then we are going to read in the amount to get change for repeatedly. Okay. So we just keep reading stuff in over and over like that. By the way, let me make sure. Okay, so then what I'm going to do is I'm going to call this function dp. And now we need to think about what were some of the base cases that we had to begin with. So one of them was if a is equal to 0. So in other words, if we don't need change for any amount of money, then we're just going to return 0. We don't have anything that we have to return in that case. Okay, there's no coins needed to make change for no dollars. Okay, if we have a case where b is less than 0, then we want to return, and I'll call it some max int. So some really big number that I'm going to have here. So I'm just going to pound define that. There's other ways you could do this, but I will do pound define max int as 1 million. Okay, just as an example. And likewise, if I ever get to a case where a is less than 0, in other words, if I ever hit a point of negative money, then I will return max int there also. Okay, so those are some base cases. That's like the base of my recursion. And so the rest of it is, I'm just going to return the min of 2 different options. So the first option is I use a coin of b, a value b. So what I'm left with is a minus val of b. And I still have all b coins to choose from, but now I've used a coin. The other option is I still have a, but I'm not going to use any coins of val b size, any more coins of it. And that's it. Okay, that's my routine right there. Okay, so it's going to make a bunch of recursive calls like that. It's just going to be a recursion. So this is just a recursive solution. This so far is not yet dynamic programming, right? We have to convert this to something that's dynamic programming. So let's see if I messed this up, which I probably did. Okay, so I'm going to read in a number like 3 coins, a value is 1, 3, and 4. And then if my amount is 6, the minimum number of coins for 6 is 2. And if I'd said 7, I could get that with 2 coins, like a 3 and a 4. If I'd said 9, I can do that with 3 coins, 3 threes, and so on. Okay? Yeah, question? Actually, it shouldn't matter if they're sorted. They should still work. Should still work anyway, but because it'll just take the minimum that you can get using one or not. But I'll try doing this and see if I get any issues with it. So 3, let's say I did it in reverse order. Then I said 6, still 2. So yeah, it shouldn't really matter. It's probably a little more efficient to sort them so that your big numbers go smaller. Okay. All right, so the problem with this approach is if I go up to a big number of these, I get a lot of calls like this. And you see 10,000, it's not even finishing. It's taking way too long. So let me try one again. Let's say I do 2,000. This might work. Nope, this is taking a really long time. Okay, it actually finished it. It got there eventually. But it was a slow process to process even 2,000. And the problem with that is that we end up solving the same dynamic programming problem multiple times. And so what we want to do is modify this, and we can use memoization if we already have this recursive function built up. We can use memoization in order to speed it up. And so if you remember, the idea here is that we're going to keep a map. So I will include map. So we're going to include a map that's going to let us store values that we've already computed. Okay, now I could store it first thing here in the DP function, but I might as well handle those like really simple cases that I need to already. But in this case, I will say something like if I will call this my DP. So first of all, let me make this thing static. So I'm going to have a static map, and I'm going to map a pair. And by the way, you have to use a map instead of an unordered map if you're using pairs as your index, just because of the way C++ works. There's like a hack that you can work around it, but otherwise use pair. If you're using pairs as your index, you want to use a map instead of an unordered map. Okay, or you need to throw some other stuff in here. So I'm going to take a pair of ints. Notice that's going to be like my A and B. And I'm going to map that to an integer, which is the value that I get. It's the minimum number. And I'll call this like my DP. Okay? And I made it static so it sticks around every time the function is called. So I say if my DP.count. So if I already have encountered AB before, so this would be make pair AB. That says if that pair already exists, so if the count is greater than 0, that means it already exists. I've already found it, so I can just return my DP sub make pair. Here, I'll put this on a new line just to make it clearer. Okay, so that means I've already encountered this pair before. I've already called this function with this pair, so it works fine. And then I call it from there, and everything goes. Okay, if that's not the case, I need to compute it, just like we were talking about before. And so I'm going to create a new variable. I'll call it retval for my return value. And at the end, I'm going to return that value. And here, instead of saying return, I will say retval equals that min. Okay, and I will go ahead and set my DP of make pair AB equals retval. So I compute what value I should return, and I store it so that the next time I come around, the next time I see this, I get to this check right here, I would say, oh, I've already found that. It's already in my map. I don't need to recompute it. I can just return the value. There's no recursive call needed. Okay, so no recursion in that case. And then I just return the retval that I have. Okay, so this is an example of the memoization. This is the sort of, this is the top-down approach to dynamic programming that we discussed last time. So if I do point change, that worked. So 1, 3, 4, and 6, I still get 2. And now if I go up to something like 10,000, notice how quickly it ran. Okay, it was nearly instantaneous. Okay, so I can run up to something like 10,000. It worked just fine. And the reason for that is I'm not recomputing all those smaller things. If you remember last time this hung, in our previous version of this did not complete for us with 10,000. Now, if I go up to 100,000, I get a segmentation fault. Why is that? Why do I get a segmentation fault at 100,000? It's because I've got too many recursive calls that because I'm going top down, I'm pushing my way all the way through, and I've got to get all the way down to where I'm like running out of coins and the value of 0. To hit that base case, I've got so many recursive calls that I get a segmentation fault. I get basically the stack overflow, the function call stack overflow. Okay, now there's something kind of cool that will happen here. So actually, let me see if I can find where that breakpoint occurs. So if I do 20,000, okay, 20,000 worked. What if I do 40,000? That worked. What if I do 60,000? That worked. What if I do 80,000? That worked. What if I now do 100,000? What do you know? It worked. And the reason is, when I first called it with 20,000, it pre-computed all those lower ones. And then when I called it with 40,000, it was able to reuse everything I'd had the first time. And so it worked there. And then I called it with 60,000. It worked for there because it didn't have to go all the way down to the bottom. So now when I got all the way up to 100,000, as soon as I hit anything below that 80,000 amount level, I'd already pre-computed it. It was already computed in one of those earlier runs. And so it didn't have to recompute it. And so I'm not going to get a overflow in the stack depth. Now, still, if I tried to go up too high from here, I'm going to get a segmentation fault if I jump up too high in one jump. Okay? All right, so this shows you one of the reasons why bottom up can work better is you don't have this problem. So in our last 15 minutes here, I want to show you how you would modify this whole thing and treat it as a bottom up example instead, if you were going to do that. So hopefully this made sense here. Let me just. Okay, so what I'm going to do is I am going to actually get rid of this call. I'm not going to be making any function calls here. Okay, none of that is needed. I can, the beginning part of this basically works just fine. I can read in all of my values just like before. What I'm going to do next is I'm going to be computing a table of values. So instead of making recursive calls, I am going to compute a table of values. So after I do all of this, I'll go ahead and I'll set up this table. So I will create a vector of vectors of ints. Okay, so it's like a 2D array. So the first element, it'll be indexed by the amount A. The second one will be by the amount B. And so I'll call this DP. And so the amount that I want to go to is whatever some max amount is. Okay, so what max amount might I want? So I'm going to pick, just as something, I'll pick 10 million divided by however many coins there are. Okay, so I want something that's no more than 10 million divided by the number of coins. So if I have something like 3 coins, then I can have amounts up to 3 million, but anything bigger is a problem. So actually, let me modify this right now. So I would say something down here like if the amount is greater than the max amount, then I want to say too big. Okay, and otherwise, I'm going to output something like this. Okay, now the difference here in this output statement is instead of making a function call to DP, instead I'm going to look this up in my array. So I'm going to have an array that just looks up the value. So I'm going to pre-compute the array. That's what I'm going to do up here. And then when it comes time to read in amounts, I'm just going to look up those amounts in this pre-existing array, where the first value is the amount and the second value is the number of coins. Okay? Notice that the size of the array is the max amount. This will go from 0 all the way up to whatever amount I actually want. And then I'm going to have to create the second part of this, like the second vector along the way. Okay, so the first thing I'll do is I will resize this so that it goes from 0 to num_c minus 1. That's the second element of the array, right? Okay. So now I've got a 2D array. I've got all of my elements set in there. And so now I need to go through and actually set what these values are. So the first thing I might do is I might say for j equals 0, j less than num_c, j plus plus. And the first thing would be I can set the amount. Remember, if you have $0, and it doesn't really matter for any j, whatever j is, the answer is going to be 0. Right? So I go ahead and I fill in that part of the table. It's 0 if it's less than or equal to that. And then otherwise, I'm just going to loop through all the amounts. So I'll do I equals, notice that set like the 0, that set amount 0. So the 0 row got set there. So I can start my index here at 1, I less than or equal to max amount, I plus plus. Okay, so again, what I'm doing here is I am filling in the elements of the table. So I'm just going to create 2 nested loops. And I'm filling in the table from the low end up to the high end. So amount 0 was set with that very first loop where I initialized that to 0. Now I'm going to do amount 1, 2, 3, and I'm going to go all the way up to max amount. And I'm going to fill in this entire table full of values. Okay, and then for each row, I'm going to go through all the columns from 0 to num_c. Okay, so here I will pick the min val, and so my default will be the max int. That's like how I'll start it off. And so the first thing I'll do is I'll check the first case, which is what if I use a coin of value b? So this is the if I use a coin of value b. So I need to have an if statement in here. If I minus val of j is greater than 0. And the reason for this is we don't want to ever index a negative value. But if that's the case, then I can set min val equals min of min val. And the other one is going to be dp sub I minus val sub j. And j plus 1. Okay. So this is my case. This is handling the case where I choose to use a coin of value j. Okay, this is like the b part of it. So I use a coin of value b. So that's what the plus 1 is here for. That shows that I have a coin that I've used. That's why that plus 1 is there at the end. The other part here, this shows the amount of money remaining, okay, which I've already computed, because notice that would be from an earlier row. So that row has already been computed, or it's possibly going to be negative. And then, yeah, and then that's that. Then the other option is if j is greater than 0, which hopefully it would be, then min val equals min of min val. And this is going to be the case where I just don't use a coin of value j. So I stays the same and j goes to minus 1. And so notice that this is where we go down. And actually, I think this should be greater than or equal to 0. not that way in my code, but I think that's right. No, sorry, has to be greater than 0. This is where we actually run through and collect something that's even smaller. Okay, and notice if we're on the last coin, that's why it's j greater than 0. We don't ever want to index into something where we get a negative index value. Okay, and then the last thing we do is we set dp of ij equal to min-val. Okay, so if you watch the video of coin change, if you go back and watch it after this, you'll see me filling in the table kind of row by row, which I hope I did it correctly. I was sort of doing it on the fly, so I might have made a mistake, but assuming I did it correctly, basically I was doing this double loop. I'm going through the amounts, I'm going through the coins, and I'm filling in all of the elements of the table ahead of time. And then now that that table is filled in, down here, all I'm doing is looking up that amount in the table. So I do dp of amount and num_c minus 1. I've already computed the minimum number of coins for that amount and that set of coins. So hopefully, if I didn't mess something up, if I compile this, make sure. Okay, so I think that's okay. I don't know what that was. Okay, so now I can have something like this, and let's first check a simple case, 1, 3, 4, and if the value, sorry, forgot to put 3. So 3 coins, value is 1, 3, 4, and then if the value is 6, okay, that is definitely wrong. Something is way, way off there. Let's see if anyone can spot the, I would offer a bonus, but I'm not really going to offer a bonus. You can get brownie points if you're the first one to notice where my bug is here. There we go. That's the problem. Okay, so it's okay to, I do need to get to that base case where it's, yeah, oh, Drew, you had it right there. Thank you. I didn't even see your comment. Okay, yeah, that should be the problem. I minus val grade greater than or equal to 0, because that is in fact how you get to the base case where it becomes 0, where the amount is 0. Okay, so now if I run the thing again, hopefully that now it works. And if I do it with 6, there's 2 coins, okay? You notice it took just a second to run that because it was having to compute that giant table that I talked about. But that table is now totally computed. So I can put in a huge number. So like last time, you might remember 100,000 broke it, and it's already pre-computed. And I can even put in, 1,000,000, and it's already pre-computed. I already know exactly how many coins I need for all of these. So no matter what I look up, now it's just an instantaneous lookup in that map. It's not going to take very long at all. Okay, so that was an example of bottom up. I'll just remind you quickly of how all of this works. So notice that we have no recursive calls. In fact, I don't need this to be, doesn't help to have that as global anymore. I can just do a, I can just stick it down here. I can, after I read everything into the value array, I go ahead and I initialize my 2D array. That's what this part up here does. Okay, and then this part is I fill in the table. First, the base case for an amount 0. Now all the other cases, we're increasing amounts. Okay, so that's what these 2 loops are going to then do is I from 1 all the way up to whatever my maximum was, then j there. And again, these are the 3 cases. This is the initial ID, initially This sort of handles the invalid check as the maxint, although you should never really run into it. This is handle the case of using a coin of value j. And the last one is handle the case of not using a coin of value j. Okay. So that's the whole idea there to sort of compute everything through there. All right, so that's exactly our time. We will have lab on Friday. Again, this week's problem set, you should have a total of 4 problems plus a challenge problem. 3 of them are going to be dynamic programming problems. Okay, so 3 of them will be DP problems like this. We will continue to see DP problems on labs all throughout the semester, so it won't be your last time. One of the problems will be a search problem. In the video, I go through binary search and ternary search. If you've never seen ternary search, at least watch the video for that. The thing about binary search is most people don't think of binary search beyond searching an array. And it's a much more general process. So I want you to understand what binary search means in general, like how you can use it to solve a problem. So I try to describe one example in the video there when you get a chance to watch that. Okay, any questions before we stop for today? All right. Well, have a good rest of the week, everyone. I will see you later.